This is something like the 5th attempt I've done to make this tutorial. None of them have gone so well. I'm taking a step back. I was going to show you how to make a parser for the interpreter that we've just been making. But parsers are too interesting to fit in a video, and I couldn't make anything that was of high quality and under 2 hours. And that's a real problem because I actually hate the video editing experience, and I give up really quickly. And it would be an even lower quality video than tutorial 11. So in this tutorial, we're stepping back. You don't really need to have understood what happened in the last couple of tutorials to understand this one. And we're going over how parsers work. And we're going over a very specific type of parser. We're going on a top-down parser, not a bottom-up parser. Bottom-up parsers are very hard to write from scratch. And as a result, you tend to use another program to write them. So in Haskell, we use Happy. In C, you might use Yak or Bison. In OCaml, Yak. And you have a domain-specific language to write them. They're fine. It's a lot of boilerplate, though. This way is extremely functional programming heavy. It really is quite a joy to do. And you can do it from first principles, and that's exactly what we're going to do. So I've made a blank Haskell project, nothing in here, and we are going to start. So in order to define a parser, we have to ask ourselves, what is a parser? Now, a parser is a program, or function, what's the difference, that takes a string as an input and returns something structured. This could be passing a file into certain formats, data types. This could be passing a programming language into an internal representation, which is what we're going to do later. All sorts of things. Anyway, classic functional programming, we can just make a type for this. So that is parser for things of type A. And now what is it? Well, it's a function, and it takes a string as an input. So the first bit is very simple. And now we have to think of a few properties that are useful in a parser. So first of all, a parser can fail. So we'll stick a maybe there. You could have a syntax error. So we need to fail in those cases. Next, parsers don't have to consume everything. We could pass the first few characters in a string, and then maybe we say the rest is garbage. And so what we want to do is we want to make it so that although we do return the structured output, we also return the rest of the string that we did not manage to pass. And that's really great because that's what we're going to use to be able to compose parsers together. Great. So that is our definition of a parser. And now I am going to change it up a little bit. I'm going to turn it into a new type. And that's so that we can really easily give it functor, monad, applicative instances later. So first of all, we need to think how a parser is a functor. So instance functor, functor, probably yes, parser, where now we've made quite a few functor instances at this point, and this one is not too tricky. So parser, and this is going to equal parser. So it's very much like the state monad so far. So what we have to return, what this is going to return, is a parser, which of course has a string as an input and outputs something of type maybe whatever. So parser s, that's our string input in the output. And then we're going to use do notation. That's what we're going to do, because maybe is a monad, so we may as well. It makes our life slightly easier. So what we're going to do first is we're going to run this parser with this input. So that is xs, perfect, and we get the structured output, and we get the rest of the string. And we are going to return fx prime s prime. And of course, because we're inside the maybe monad, all of that error handling is handled for us by the definition of the monad. This do is in the maybe monad, and that's perfect for us. Monads compose fantastically, and we can swiftly move on to our applicative instance. So, pure This isn't too bad. Let me do the indentation. So we're returning something of type parser. It takes a string as an input, and we are going to just return X and that string. So we're passing none of the string and sticking an X as our passed value. So that's our pure instance. And then this one is always the tricky one. Parser F, sort of applied to, I still don't know what that thing's called. Parser X, it's going to be parser S. And we'll use do notation again because it's very useful. So we're going to kind of unwrap from our maybe monad the first parser, so fs, and then we're going to unwrap our value x prime s2, and that's going to be x of s1. So we're kind of chaining what we haven't consumed in the last parser into the next one. And then to finish off, we are going to return f prime of x prime and the remainder of the string. So let's see, do we rate my ability to code live? We do. There we go. So we've got an applicative functor definition and a functor definition. And of course, we finally need to go about defining our monad. So I'm going to quickly make a helper function, I think. I have already got something called run parse. Doesn't matter. I'm not going to make a helper function. I take it back. I've pretty much already defined it up here. So instance monad of parser where. So we don't need to define return because we've defined pure. And we'll go parser x bound to f, yes, equals parser backslash s, exactly the same as before, and it's do notation. So the first thing starts as they all go. We get our x value and our s prime value from the original parser with the input string. And then we're simply going to, I guess we're going to just run that parser. So that is going to return something of type parser b, but we're already inside a parser, so it's kind of parser b. So we need to unparser this. So we're going to run parser, and that is going to take this, which is a parser, and then I'm going to apply to it s prime, because I don't want something of type parser, because I have something of type parser and I have the string here. I want something of type maybe a string, so I need to give it an s. So hopefully that worked. Nope. I spelt monad wrong. It's always a spelling mistake with me. Always a spelling mistake. There we go. So it's probably the most complicated monad we've made so far. Now what we're going to do is we're going to investigate some of the other kind of extended monads in Haskell. And the first is monad fail. No, we've already covered that in another tutorial. Yeah, we have, haven't we? Because we did it with the either. Well, don't worry about me talking about that. Let's just define a monad fail instance. I need to keep track of what I've already done. So this is just fail of s is just going to be parser s to nothing. I've got s twice. Well, I don't actually care about that one. Perfect. It's just going to be the failed parser value. So that's okay. No errors yet. We're on a roll. Monad plus. Now that's something I've definitely not talked to you about, or at least alternative. So what we need to do is we need to talk about, yes, alternative. So the best thing to do to understand this is to info it. Hopefully I don't have to, nope. Have I spelt it right? Alternative, nope. Import control.applicative. There we go. So I need to remember to import control.applicative. So alternative is, it's a type class. It's a constraint on a type, and it's a constraint on the same sort of types that we've had before. Its kind is type to type. And here we have the definition. So we have a whole bunch of functions here: empty, this one, some, and many. And let's see if we can work out what they do from their types. So empty just seems to be a blank sort of non-value, sort of a unit value, if you like. Now this is sort of, how would I describe this one? I guess it's sort of like a trying type. So what we do is we try this. If it fails, which I imagine means if it's the empty value, then we return this. If not, we return the original thing. So it's kind of try this. If it doesn't work, try that. So this or that. And that's why it has the universal computer science or symbol inside it. Now, some and many. Okay, some. Yeah. So some is kind of like one or more A's. So we give it an applicative functor value, and it gives us lots of them. And for things like maybe, which is an applicative functor, that doesn't make any sense. But it does make sense for a parser. And that's because a parser, although it's a type, like maybe, it's kind of a doing type. It's like a verb. If this was a natural language, it's doing something. It's taking a string and returning something. And so some, and then a parser, is going to return us the parser that continuously tries and tries and tries to parse until we have a list of things, if you like. Now, many is the same as some, but if this fails, then it returns this in the empty list. So we're going to become quite acquainted with these because we're going to use them quite a lot. So instead of importing it, let's just define it. Yes, so class applicative f alternative f where. I think this is class syntax. And then we had empty, which is of type fa. We had this bad boy, which was of type fa to fa to fa. We had some, drop that bracket, which was of type fa to f list a, and we had many, which was of the same type. So is it going to complain? No. Good. We've defined our class successfully. Now let's see if we can make an instance of this for our parser. Yeah. So we can start with sort of standard definitions. So in the real alternative world, we have a minimal definition, which is quite minimal. I can't quite remember how much we have to define. I'm going to quickly Google it. Control.applicative. Let's have a look. Sorry about this, very unprofessional. But it turns out you don't need to store all of this information in your head. So the minimal complete definition is just empty and this. And that means we should be able to give default definitions for both some and many. So let's have a look at that. So I'm pretty sure if you want to give a default definition, you just define it in the class. So sum of v equals... Now, I actually remember how this is defined in Haskell, so this is why it doesn't look very much like my code. So, where many v equals sum v or pure that. Okay, and sum v equals... And then we have some lovely applicative notation here. Absolutely love that. So this is beautifully recursive or horribly recursive. Doesn't matter how you look at it. So what we're saying is sum v's is equal to sum underscore v, which is this line. And you see we're constructing a list within a functor, an applicative functor. And we're saying the first thing is v, up here, and then after that, because it's the list joining operator, we have many v's, which is of course recursively defined as sum v, which means we're going to stick this v in again, followed or pure if that fails. So you'll notice that if we went for the many v first, then this could fail and we just return the empty list, whereas if we go for sum v first and this fails, then the whole thing fails. So that's how we get the difference. So the many v one is very similar. That's it. It's a copy and paste jobby. Absolutely easy. So a little bit hard to get your head around, I find at least, what's going on here. But really, it's just within a functor making v, which of course makes no sense for something like maybe, because, you know, many just 10 becomes just and then an infinite list of tens. What's the point? Yeah, what is the point? Well, but it makes a lot more sense for parsers, and that's because it's not a value, it's a function. So it's pass until failure. So let's see if our default definitions worked. Yes, good. We are remembering a lot of Haskell syntax today. Lovely. I'd forgotten how you do default definitions, but it's nice that you just define it. So now let's use our class, our alternative class, and let's give an instance for alternative. So instance alternative parser where. So we need to do an empty, which is going to be exactly the same as fail. And we're going to do the whole parser, I need to do this in brackets, parser x or parser, apologize, parser y. So what we're going to do here is we need to work out if this has failed. So in order to do that, we're going to construct a new parser. So parser, that's the string, and the first thing we're going to do is we're going to go, we'll go new line, case parser, no, not parser, xs of. Now, if it's, I don't need brackets there, if it's just, and then some values, then we're just going to return those values. So we'll just return just x. Now, if it's nothing, then we're going to return y of s, same input as last time. And I think that's going to type yes. So to reiterate, we've got our two parsers. We run the first parser here, if it succeeds, we just return the output. If it doesn't succeed, we run the second parser and return the output, regardless of whether it fails. If they both fail, the whole thing's going to fail. Perfect. So, what does this allow us to do? Well, it allows us to do all sorts. So let's start by, let's make some parsers. So, how should we go about this? Yes. Okay, we'll start small and build up. I mean, that is how you go about these things. So normally this stuff is buried in the library, but nah. I'm going to steal the function names of Ataparsec, which is the parsing library we'll probably use next time. It's exactly the same. So let's make a character parser. And that's going to be its type. So, no, it's not. It takes a character, and what it returns is a parser of that character. So, the character is going to be C, and then what we return is we're going to return a parser, and I'm going to pattern match. Should I pattern match? Maybe. Yes. No, I'm going to do... Okay, sorry. Lost in thought there. I'm going to define another part. I'm going to define a sort of an unwrapped version of this. I think it's a much nicer way of doing it. So char p of the empty list is going to be nothing. Oh. Char p of... So I'm just doing this because I'm turning it into a new function just because it's easier to pattern match. It's cleaner to pattern match here instead of having to deal with this parser constructor. So now what we need to do is we need to go, is x equal to c? And if the answer is yes, then we will return just, and then c x's. And then otherwise, we will return nothing. So, got to make it a line. Perfect. Okay, so that is our character parser. So let's test it out. So if I say parse d equals char d, then run parser, and then we have to give it the parser, parse d, and then we have to give it an input string. And if I give it just a d, then it manages to successfully parse that d. If I give it, that's also a d, an f, then it fails. So we've made a parser that can parse, that can parse a single character. Now that might seem small, but we're going to build up quite quickly. Actually, before we leave that, how would we go about making one that does uppercase or lowercase d's? Because if I parse an uppercase d, it's... I forgot to reset it. Nope. Parse d, and then let's do the uppercase d again. It fails. So what I can do is I can use that alternative. And now it succeeds on uppercase and lowercase d. So we can construct parses this way using this alternative operator. Now, how about strings? It'd be nice if we could match strings. So string. And that's going to be string to parser string. So this one is a little bit magic actually. And you're going to see how quickly the sort of the abstractness of Haskell kind of really, what's the word? Abstracts everything away. And that's it, actually. And I will prove it to you. Oh, it's not called parse char. That was what I was going to call it. It's just char. Let me show you. So I'm just going to call it p equals string, and then my name, James. Now we can run parser p of James, and it matches. If I don't give it a s, then it doesn't match. If I give it two s's, you'll see that I have a little bit left over here. If I say Tom, then nothing. So how did that work? How did that two-word function manage to take our char parser and turn it into a string parser? Well, it's just because the Haskell definition of a string is a list of characters. And what we do is we do mapm. So think about the definition of mapm. So mapm of this is return this. I need the function that we're mapping. And mapm f of x cons x's equals, and then what we do is we say sort of x prime equals f of x, and we say x's prime equals map m f of x's, and then we return x prime x's prime. So that is the definition of mapm. And so first of all, what is our input? Well, our input is this string, which is what we're matching against. So this string in the example I gave you said James. And so what we did is we used our character parser and we created this. This is a character parser for the capital J. And then this becomes a character parser for aims. And we return it in a list. But of course, the do notation, the rules of do notation, given that we've defined bind however we've defined bind here, it's essentially like passing a string around. We pass the string here, it matches on the J, we then pass the string here into the next thing, and it passes on the A, and then the next thing, the M, the next thing, the E, the next thing, the S, which means that list, that is a parser list of characters, which is a string. And so there we go. We can really quickly build up parsers. Perfect. Yeah. So let's see if we can use many now. So we might want kind of a, so SS, skip space. And that is a parser of strings. And what I'm going to do first is space. Let's define space. Capital P, parser of a char. And so space we set equal to char f, not what f, space, char, oh, I need my or. Why did I say f? Char /n or char, you get the message, /r, or char /t. I'm going to stop there, and then we say skip space equals many, because there might be no space, many space. Okay, and now we can do things like we can say parse hello world equals string hello, and then skip space, and then world. Now, it might not be completely obvious what this is doing. What I might do is this. I know I haven't explained what that infix is yet, but it will become clear in a second. And it's gonna give me an error telling me to enable. Oh, I forgot a language extension. Oh, it didn't. Well, that's strange. Who knew? Anyway, it's called parse hello world. So parse hello world, run parser. Now I can say hello world, and it gives me a tuple. But I can just keep on increasing these spaces in between, and it does not change the output. So let's go over what went on in this line. So I'm clearly using this applicative form that we're all aware of. Now, this is something else you can do with applicatives. And it essentially says, this one says, do this, and if it succeeds, do this, but then return that. Okay? And if any of these fail, the whole thing will fail. And it goes the other way around. If I did this, I'll end up with just some space. And it says, do this, and if it doesn't fail, do this, and if it doesn't fail, return it. So it's the other way around. So this time I'm going to get loads of space in the first one, and world in the second. Lovely. Fantastic. So we can just make parsers out of this. I'm trying to think of I mean, you can make combinators for numbers. They're not so hard. You just need to match on the numbers, and then you need a smart way of concatenating them. Maybe we could try that. So parse int. So we're going to go parse int prime first. And that would be parse. Oh, what's going on? Parse int prime equals, and then it would be, oh, missed, char 0 or char 1, oh, missed, or char 2, and then I'm gonna overshot, and then that's going to be 5, 4, 3, and then why am I finding this so difficult? 8, 7, 6, and then 9. Okay, so that's going to pass a single integer. And then parse int. Oh, these are all chars. So I might change this to parse int char. And then parse int. I've done it again. Parser of int. It's going to be sum parse int char. And now we have sort of a list of characters which have integers in. So we need a function which is going to be string to int, and that's going to take in a string and output an integer. And we can guarantee that the elements of this string are in here, which is nice. So string to int of, so oh, what am I doing? Oh, empty list, we need that case. So what we're going to do is we're going to say that's going to be str to int times by 10. Yep. And then plus sorry, string to int. No. So that's going to be how. Never code live. You always hesitate over the easy things. Yeah, what I'm going to do is I'm going to add an accumulator. So it's kind of like a left fold here. So that's going to be str to int x's of ac times 10 plus, and then char to int of x, char to, and then this of course is just going to be ac, and then we can do this mapping here. So that's str to int. I'm going to move this here. We've got to the mumbling stage of the tutorial. Always comes, doesn't it? Trying to speed code like that. And then this is a really boring function. So can I do this? Yeah. I've only done 7, but it's a start. No, that's definitely slower than just. Okay, and then 7, 8, 9. Oh no. 9. Okay. Right, well, we'll see how that goes. Nope. Multiple declarations. Pass int char. Huh? Where are my multiple? What? Ah. Type. Oh, I forgot to change the way round this went when I changed the input order. And there we go. So, run parser, and then parse int, and then there we go. And that's an integer in there. And then if I add an f, it didn't manage to parse those. If I stick an f at the beginning, it's not going to manage to parse that either. So we've successfully made, and we can check the type of that. It is of type int in there. So we've successfully made an integer parser. And you can use this to parse programming languages and anything really. This method I use a lot at work to parse messages in TCP protocols, for example. But I have written fully blown programming languages that use this as the parsing method. And that's going to be all for this tutorial. I hope it was bearable. I hope the quality's coming back up again. And I'll see you for tutorial 13, where we're going to apply what we have learnt here and make a parser for our interpreter. Okay.